In section 3.5, we're going to continue finding derivatives, and we're going to continue using our product rule and quotient rule and chain rule. What we're going to do here in 3.5 is we're just going to add some new functions that we're able to find the derivatives for, and that is our 6 trigonometric functions. So there are 2 of them that we're just going to memorize. And I'm not going to go through the whole process of proving these for you, but there is a proof for the derivative of sine in our textbook on page 167, I believe it is. No, 165. On page 165, there is a proof using the limit definition on how to find the derivative for sine. We're not going to do the limit definition for these problems, but what I am going to tell you is that you need to know the derivative for sine and cosine. Those are just the 2 most basic, and if we know those 2, we can come up with all of the other ones. So the derivative for the sine of x, so x is the angle. Hopefully you remember that from trigonometry class. The derivative for the sine of x is the cosine of x. That is one that we just need to know. And the derivative for the cosine of x is negative sine of x. So the derivative for sine of x is cosine of x, and the derivative for cosine of x is negative sine of x. If we know those 2, we can technically figure out the derivatives for our other 4 trig functions using quotient rule. And there's also a pattern if you don't want to have to use quotient rule to figure them out every single time. Hopefully we work enough problems and we study enough that we can just remember all 6 of these trig derivatives, and we don't have to do all the hard legwork every single time of deriving them every single time. But there is also a pattern, depending on how much trigonometry you remember, to how these derivatives work, and I'll go through that pattern as well to hopefully help you to remember these trig derivatives, because they are worth memorizing and knowing, especially if you're going to go on and take more calculus classes. We do a lot with these trig derivatives in calculus 2. So these 2 we just absolutely need to know, that the derivative for sine is cosine and the derivative for cosine is negative sine. So if we want to find the derivative for some of the other trig functions, and I'm not going to go through this whole process for all of them, but for example, if we want to find the derivative for tangent, well, you should have learned in trigonometry class that the other 4 trig functions can all be written in terms of sine and cosine. So we can write tangent in terms of sine and cosine. So tangent is equal to sine divided by cosine. And if we write it that way, then I can figure out the derivative for tangent by doing the quotient rule, because there is a function of x in the numerator and there's a function of x in the denominator. So our quotient rule says, I'm going to let the top be f, and I'm going to let the bottom be g, and we need each of the derivatives. So f prime is cosine, g prime is negative sine, and remember we crisscross these. We do f prime g minus g prime f for our quotient rule. So the derivative is going to be f prime g, that's cosine x times cosine x, and then minus g prime f, so negative sine x times sine x, all over g squared. So cosine squared. And we're going to simplify this as much as possible. So cosine times cosine, that's cosine squared. Sine times sine is sine squared, and we have a double negative here, so that's going to be plus sine squared. And in the bottom we have cosine squared. And be careful, because those cosine squareds do not cancel out because of the addition there in the numerator. We cannot cancel the cosine squareds. What we can do, though, is we can use a trig identity. Cosine squared plus sine squared is a Pythagorean identity for 1. So we just have 1 over cosine squared. And that is actually equal to a different trig function. Cosine in the denominator, whenever possible, when we're working with trig, we don't want to leave it in terms of a fraction, because a trig function in the denominator is always equal to a different trig function pulled up to the numerator. So we can pull cosine up to the numerator if we remember what the reciprocal function is for cosine, and it is secant. And that is completely simplified. So the derivative for tangent is secant squared. So we can add that to our list of trig derivatives. And I figured that out just by writing tangent in terms of sine and cosine and working through the quotient rule. And we can do that for all of them, because cotangent can be written as cosine over sine, secant can be written as 1 over cosine, and cosecant can be written as 1 over sine. So I'm going to do one more like that. I'm going to do cosecant. We are going to find the derivative for cosecant x. So really all we know and all we have to really memorize is the derivative for sine and cosine. Every other trig function can be written in terms of sine and cosine, and we can go from there. So cosecant is equal to 1 over sine. And I am going to use the quotient rule. That's one way to do this. I'm going to use the quotient rule to find the derivative. There is another way to do this, but just to be consistent, I'm going to use quotient rule. So my numerator, f of x, is 1. My denominator, g of x, is sine x. F prime is 0, because f is a constant. Derivative of a constant is 0. And then g prime, since g is sine, g prime is cosine. And then we're going to crisscross and set back up our quotient rule. So quotient rule says do f prime g, that's 0 times sine, minus g prime f, or fg prime, the other diagonal there. So 1 times cosine, and all over the original g squared, so sine squared. And then we want to simplify this as much as possible. Well, my first term has 0 times sine. That's just going to zero out. The whole first term is just equal to 0 because we have times 0. So this simplifies to negative cosine over sine squared. And there's probably lots of different ways that we could write this. We definitely don't want to leave it as a fraction, because we could pull sine up to the numerator as a different function. There is one preferred way to write this, though. And what we're going to do is we're going to separate those signs. And we're going to keep one of them with the cosine. And we're going to separate and write another one by itself. Because sine squared is sine times sine. So it's still multiplication. I still have sine times sine in the bottom. Now cosine over sine is cotangent. And then 1 over sine is cosecant. So the derivative for cosecant is negative cotangent cosecant. And again, I got that just using the quotient rule. But you have to remember how you can write all four of those other trig functions using sine and cosine. And then once you get your quotient rule all set up with your f primes and your g's and your g primes, how you can use everything you remember from trigonometry to simplify it. So I'm not going to go through all four of them. What I'm going to do is I'm going to make the list of all six of them for you. And then I'm actually going to go through the pattern, and then we'll do a bunch of examples. So our 6 trigonometric derivatives all together in one list. And I'm going to write these a certain way, and it's going to help out my pattern that I'm going to show you. So the derivative for sine is cosine. The derivative for cosine is negative sine. The derivative for tangent, we saw, is secant squared. The derivative for secant, we haven't done that one yet, but the derivative for secant is secant times tangent. The derivative for cotangent is negative cosecant squared. And the derivative for cosecant, which we just did, is negative cosecant cotangent. I think we switched those up here, but it doesn't matter. It's multiplication, so they can be written in either order. So those are our 6 trig derivatives. Those first 2 we need to remember. It's actually good to remember all 6 of them, but in a pinch, if we don't remember those last 4, we could figure them out if we write those last 4 trig functions in terms of sine and cosine and do a quotient rule. We can figure them out. So there is a pattern here. And sometimes when I explain it, people get it, and sometimes when I explain it, people don't. And in order to see and understand the pattern, you have to know your Pythagorean identities from trig class. So let me write those down really quickly. So the most basic that pretty much everybody remembers is that sine squared plus cosine squared equals 1. But there's actually 2 more Pythagorean identities. And we can get those other 2 Pythagorean identities if we go through this first one and we divide everything by cosine squared and simplify. So if I divide all 3 of those terms by cosine squared, I will get tan squared plus 1 equals secant squared. Or if I go back and I divide everything by sine squared, I get 1 plus cotan squared equals cosecant squared. So there's actually 3 Pythagorean identities. They're all based on the first one, but technically all 6 of your trig functions belong to a Pythagorean identity. So our first one involves sine and cosine. And if you look back up at our derivatives, the derivative for sine is cosine, the derivative for cosine is sine. Those 2 derivatives are always going to go back and forth between each other. So if you remember the Pythagorean identity, you remember that sine and cosine go together in a Pythagorean identity, then you can remember, oh, well, the derivatives for sine and cosine always go back and forth between each other because they are together in a Pythagorean identity. The same is true for tangent and secant. tangent and secant belong in a Pythagorean identity together. And if you look at the derivatives for tangent and secant, their derivatives always stick together. The derivative for tangent is secant squared. The derivative for secant is secant tan. And we can just keep going back and forth and back and forth and back and forth, and their derivatives will always stick together. The derivative of a tangent involves secants. The derivative of secants involves secants and tans. They never stray off into one of the other Pythagorean identities. They never throw in a cosecant or a sine or anything like that, or a cotangent. They always stick within their own Pythagorean identity. And then this last one involves cotangents and cosecants. And if you look at those derivatives, they do the same thing. The derivative for cotangent is negative cosecant squared. The derivative for cosecant is negative cosecant cotangent. Those derivatives always stick within their own group. So the pattern is beneficial if you already know the Pythagorean identities. If you don't know the Pythagorean identities, this might not be very helpful. So that's one of the pieces. That's one of the pieces of remembering the derivatives. There's more parts to it, though. So that at least will help you to figure out what functions you should be working with. The other part, there's two more parts. Actually, I think there's three. Any trig function that starts with the letter C, and obviously this is not a very scientific one. Any trig function that starts with the letter C is going to have a negative derivative. The derivative for cosine is negative sine. The derivative for cosecant is negative cosecant cotangent. The derivative for cotangent is negative cosecant squared. If your trig function starts with the letter C, the derivative is going to be negative. Another part to the pattern is if your trig function contains the word tan. So both of these contain the word tan if you say them all the way out. So tangent and cotangent. So look at those derivatives. What do they have in common? They both have a square. Both of your tangent functions have squared derivatives. Both of the tangent functions have squared derivatives. And then these other two guys, which are the reciprocals of our basic functions, they both contain themselves and their Pythagorean partner. So what I mean by that is, so the derivative for secant contains a secant, and then whatever guy was down here with them in the Pythagorean identity. So the derivative for cosecant is going to contain a cosecant, and then whatever guy is down here in his Pythagorean identity. So there's a bunch of little pieces to it, but sometimes knowing a few of those little pieces is helpful instead of having to memorize just 6 completely random brand new derivatives. So we're going to do a whole bunch of examples that might involve product rule, quotient rule, chain rule, but now they're also going to have trigonometry in them. They're going to have trig functions. One thing that I want to mention before we start some of these problems is that all of these examples that we've seen so far, the angle has always been x. Now we could replace it with a different letter. It could be t, it could be theta, it could be anything. But if it's ever anything but just a single linear variable, then you're going to treat it like a chain rule. Then it's going to be considered its own function. So if I were to put 2x in there, then we would have to do the chain rule. Or if I were to put 5x minus 2 in there, then we would consider it a chain rule. So if the angle, now I don't want to say if it's anything but an x, because we can use different variables, but if the angle is anything but a single, that means no coefficient. Linear, that means no exponent. Variable. Then you have to use chain rule. So let's start with one of those, because those are pretty easy. And all we're doing here is just finding derivatives. So calculate each derivative. We want to find the derivative for the cotangent of 5x. So our angle is not a single linear variable. It is linear, but it's not a single variable. It's 5x. So we've got to treat this as an inside and an outside. So the inside function is 5x. The outside function is cotangent. So the chain rule says you're going to start with the derivative of the outside function. So the derivative for cotangent, well, it starts with a c, so it's going to be negative. Cotangent has a Pythagorean identity with cosecant, so I know it's going to be cosecant. And anything that has the word tangent in it is going to be squared. Now, anytime you are working with trigonometry and calculus, you never change the angle. The only time you are ever allowed to change your angle is if you are going to apply an identity, such as a double angle identity. If you want to use a double angle identity to simplify something, then that's perfectly fine. I'm never going to ask you to, but you never, ever, ever change the angles in the problem. So if your trig function has a specific angle, then every single thing that you do in that problem after that, all your trig functions should always continue to have that same angle. So the derivative of the outside piece, cotangent, is negative cosecant squared. And we keep the exact same angle. And then chain rule says you have to multiply by the derivative of the inside function, which is 5x. The derivative of 5x is 5. And the way that we wrote this when we did chain rule is we said we're going to let u equal 5x, and then y equals cotangent of u. du dx equals 5. dy du equals negative cosecant squared u, but we have to write that back in terms of x. And chain rule says multiply them together. And that's exactly what we got up here. I just did it quicker without having to write all of this stuff out. So the fast way to do chain rule is you do the derivative of the outside piece times the derivative of the inside piece. So our final answer is negative 5. So I don't want to leave that 5 at the back. Usually we write coefficients at the front. Negative 5 cosecant squared of 5x. This one's a tricky one, but I want you guys to see tricky ones. So then when you see easier ones or later, then they'll be really easy because you've already seen all the tricky ones. But this one technically is like a double chain rule. This power right here is like a lazy mathematical convention so that we don't have to do extra parentheses. But before we do the derivative, we really do want to see those parentheses. It helps us to decide where the inside functions are and the outside functions are. So that power of 3 right there, it really means the whole thing is being cubed. So I want to rewrite this so that I can actually see that. So this is the sine of x squared minus 2, the whole thing cubed. And that's what I want the derivative of. So there's like 3 layers to this function. There's the cubed, that is the outermost layer. There are no parentheses holding that in, besides those brackets that say do the derivative. So this is our outermost layer here. And when we do the chain rule, we always start with the outside. So that's going to be our step number 1. If you move in 1 layer of parentheses, only 1 layer of parentheses, the next function you see is the sine function. So that's going to be our step number 2. And then if you move in another layer of parentheses, you see the x squared minus 2. So that's going to be step number 3. So we really have 3 different derivatives to take here. And as we take those derivatives, only worry about the one derivative that you're taking. Leave everything else inside of it alone. So the first derivative we need to start with is the cubed. Don't worry about what's inside of it. Just think about how you would take the derivative of something that's being cubed. If I was taking the derivative of x cubed, I would do the power rule on it. So the power rule says bring the old power out front, and the new power is 2. But everything on the inside has to stay the same. We're not messing with that stuff yet. We'll get to that in a minute. So that's the derivative that we would do for a cubed. Old power of 3 out front, new power of 2. But everything inside stays the same. And then we can multiply and move in a layer. The next layer, layer number 2, is the sine. So now we'll decide how we do the derivative of a sine. Well, the derivative of sine is cosine. Everything inside of it stays exactly the same. And then we move in a layer. If you move in a layer, you get to the x squared minus 2. Well, the derivative of x squared minus 2 is 2x. And that was the innermost layer, so we don't have to do anything else. And then we'll just try to clean this up a little bit. That's a sine squared and a cosine, and the 3 and the 2x can get multiplied together. So this is really 6x sine squared of x squared minus 2 cosine of x squared minus 2. So we can apply that chain rule for as many embedded functions as we want. You just start at the outside and do them one at a time. And as you do them, everything inside stays the same. So we're going to do just a couple more. We'll do one that involves product rule, and then we'll also do a higher order derivative. And actually, I think this will just be C. Yeah. So let's find the derivative for e to the 4x tan x. So this is a product of 2 functions of x. We're multiplying together e to the 4x, and there's a x in there, and tan x, there's an x in there, and these 2 things are being multiplied. So anytime you're asked to do a derivative and you have 2 functions with x being multiplied together, you have to do product rule. You can't just take the derivative of each piece separately. So we have to identify our f and our g and take their derivatives individually. So f, I'm going to say, is e to the 4x. And remember back in, I believe, section 3 or section 4, we said the derivative for e to the 4x is going to be 4e to the 4x. And that's actually a result of the chain rule. But we wrote out a little separate rule for derivatives of e to the kx. And then our g of x will be the tan x. G prime, if you think about the pattern, tangent, it doesn't start with a C, so it's not going to be negative, it's going to be positive. Tangent goes together with secant in a Pythagorean identity. And remember, anything that has the word tangent in it, its derivative is going to be squared. So G prime is secant squared. And then for product rule, we crisscross, and then we'll put a plus between. So our derivative is going to be 4e to the 4x tan x plus e to the 4x secant squared x. Easy as that. Same stuff we did in the last couple sections. We're just introducing the trigonometry is all. The derivative of secant t over sine t minus 1. The derivative of secant t over sine t minus 1. And I'm going to warn you right now, I just made that one up, and so this might get ugly, but we'll see what happens. And I don't want to do equals yet, because we have to recognize that this is going to be a quotient rule. We want the derivative with respect to t, and t is our independent variable here. So we don't do this any different than any of the rest of the problems. We're just using a different letter for the variable. But it is going to be a quotient rule because there is a function with t's in the top and there is a function with t's in the bottom. So we're going to want to write out our f of t, which is our numerator. That's our secant t. And its derivative, well, secant starts with an S, not a C, so it's going to be positive. It's the reciprocal of one of our basic functions, so it's going to have itself and its partner. Secant goes together with tangent. So it's going to be secant t, tangent t. Our denominator is g of t. That's sine t minus 1. And g prime is cosine t. And then we crisscross. And quotient rule has subtraction in it. So this is going to be secant t tan t times sine t minus 1 minus secant t times cosine t all over the original g squared. So sine t minus 1 squared. And we'll try to clean up that numerator a little bit so this stuff can get distributed. That is secant t, tan t, sine t, minus secant t, tan t, minus secant t, cosine t. Don't multiply out the bottom. I would always just leave that as g squared. And there are actually a few things we can do in the top to fix that. There are several things. Now, secant and cosine, those are reciprocal functions, so they actually multiply to make 1. And then this secant is 1 over cosine. Tangent is sine over cosine. So I've got 1 over cosine, sine over cosine, and sine. If you multiply all that out, you actually end up with sine squared over cosine squared, which is tangent squared. And I don't know how much we really want to mess with this. At this point, it's just a whole bunch of trig simplification. I'm not going to do anything else. We're basically just concerned with the derivatives. So that's plenty. But anytime we can simplify it, if we have to do anything further with our derivative, like finding slope, or in chapter 4, we're going to be finding all sorts of different characteristics on the graph of the function using our derivative. And anytime that we can simplify our derivative as much as possible, it's going to make using that derivative a whole lot easier. So that's one with the quotient rule. And I want to look at one more. And this is one that is going to require us to do a higher order derivative. So let's find the second derivative of, let's see here. Let's find the second derivative for sine x times cosine x. The second derivative for sine x cosine x. So we're not done until we have applied all the rules twice. So we have to get our first derivative first. Technically what this means is take the derivative of the derivative of sine x cosine x. So we're going to work on the inside part first. We're going to work on the first derivative. And then once we get the first derivative, we will then do the derivative again. So this is a product rule. We've got sine x times cosine x. So f of x is sine. F prime is cosine. G of x is cosine. G prime is negative sine. So that's my outsidemost derivative. And I'm going to now write the answer for my inside derivative. So remember we crisscross here. So I'm going to do cosine times cosine, that's f prime times g, which is cosine squared. And then plus sine times negative sine is really going to be minus sine squared, because I'm going to be adding a negative. This is my first derivative here. Since we want second derivative, we've got to go through the whole process again. Well, we're seeing those powers again, so really it's better to rewrite those powers outside the parentheses. It's easier to see the chain rule. Anytime you've got trig with a power, it's easier to write it with your parentheses and see the chain rule. So both of these, we've got to do the chain rule. The derivative of the outside times the derivative of the inside. They are separated with subtraction, which means I can do their derivatives separately. So first, for cosine squared, the squared is on the outside. So I'm going to start with just how I do the derivative of the square. So for the derivative of the square, the old power comes out, and keep the inside exactly the same, and subtract 1 for the new power. That just takes care of the derivative of the outside, and then we have to multiply by the derivative of the inside. The derivative for cosine is negative sine. And then I'll bring down my subtraction. And then I'll do the same thing for the derivative of sine squared. First, take care of the outside derivative, which is old power comes out front. Don't change the inside yet. We'll take care of that in a minute. Subtract 1 for the new power. So that's the derivative for a square. 2 out front, new power of 1. And then multiply by the derivative of the inside. The derivative of sine is cosine. And we'll clean this up a little bit and simplify. This really is just negative 2 sine x cosine x. This is minus 2 sine x cosine x. Those are like terms. So we could really put them together. This is negative 4 sine x cosine x. That is our second derivative, because we actually went through the derivative process twice. The first time we went through the derivative process, we did product rule, because the original function was sine x times cosine x. So we went through product rule, and we got this. That was our first derivative. Then our second time through the process, we had to do chain rules. And then when we simplified, we got this, negative 4 sine x cosine x. That is our second derivative. Everything we've been doing with these derivatives in terms of finding tangent lines and slopes and instantaneous rates of change and all that stuff, using product rule, quotient rule, chain rule, everything's exactly the same. The only thing new here in this section is we have introduced some new functions, our trigonometric functions.